This is the second lesson of Chapter 5. In this one, we're going to concentrate on the ideal gas law. So we start off with three containers with different gases in them. We have helium, nitrogen, and oxygen. And each container has the same volume, 22.4 liters. And they're measured under STP conditions. Remember, STP means 0 centigrade and standard pressure. Now, one thing we would notice about these, their masses all are equal to the molar masses. So when we have 1 mole of any gas occupying 22.4 liters at STP conditions, then we know exactly how many grams of that gas we have. So now we have a link between the mass of the gas and its volume, but this is only at STP. If the temperature and the pressure were different, the 22.4 liters would be different. So if we had a warmer temperature, we might have like 24 liters, something like that. But we can use the 22.4 liters and the fact that we have 1 mole of the gas at STP to answer some simple questions. So let's take a look at a few of those. We could find out what's the density of oxygen gas at STP. All we need to do is know its molar mass and its molar volume. So for the molar mass of O2, we would have 32 grams, and the molar volume is 22.4 liters. And so we can use these two in our density formula. And so we find then that the density of oxygen gas is 1.43 grams per liter at STP. So we can find the density of any gas at all at STP. All we have to do is have its formula and a list of its own equates. Works out pretty easy. So here's our little formula then. D at STP equals molar mass divided by molar volume. So here's a question you might want to answer. Let's see if you can do this one. What's the volume in liters occupied by 49.8 grams of HCl at STP? Now, HCl being a gas now, and they're going to say, well, it's an acid. It's only an acid after it reacted with water. So let's say we have HCl gas. So 1 mole of HCl would occupy 22.4 liters at STP, and 1 mole of HCl would weigh 36.5 grams. This is all we need to know. Now you notice we have more than 36.5 grams, so that tells us that the volume is going to be more than 22.4 liters. So what we're going to do is we're going to find moles of HCl first, and then we're going to find liters. So to find moles of HCl, you take the mass that was given and divide it by the molar mass. So we get 1.36 moles of HCl. And then we just have to multiply that by molar volume, 22.4 liters per mole, and we get 30.6 liters. It's pretty simple. Now what we can also do is derive a gas law using STP conditions. So I'm going to start off with looking at my gas laws a little bit differently than we had in the previous example. Boyle's law can be written as PV equals a constant. Charles' law, V over T equals a constant. Avogadro's law, V over N equals a constant. Now if we combine them all together, we get PV over NT equals a constant. And rearranging this a little bit, we can get PV equals N times the constant times T. Now instead of writing the word constant all the time, we can replace that with a letter. And I'm going to pick the letter R. So I get then PV equals nRT. And this is known as the ideal gas law. So we're going to use this gas law anytime we have just one set of conditions. There is no ones or twos here, just one set of conditions, and it really combines everything that we need. Now one thing about ideal, what do they mean by that? Well, some gases are what we call ideal gases, and then other gases are more like real gases. So let's take a look at the difference between the two. Real gases have a mass. An ideal gas has no mass. Real gases have attractions for each other, so they'll pull at each other and probably not occupy the volume you might think, whereas ideal gases have no attractions, so they always occupy the volume that the gas laws would predict. A real gas could condense to a liquid if you cooled it enough or pressurized it enough, whereas an ideal gas would never change to a liquid, no matter how much you pressurized it or cooled it. Real gases obey the gas laws sometimes, just like you obey laws sometimes. But the ideal gases would always obey the gas laws under all conditions. So under what conditions would real gases not obey the gas laws? Well, anything that puts the particles close enough together would cause them to not obey the gas laws. That means high pressure or low temperature. Now for ideal gases, the noble gases are closest to ideal. Probably helium is the most ideal of all of them. And so here are a couple of examples of real gases, CO2 and ammonia. And here we have a couple of noble gases, neon and helium. All right, so let's take a look at the formula now. PV equals nRT. I'm going to show you how we can derive the value of R. And once I show you that, we're going to use the same value all the time. So you'll never be asked to derive it again. Just want you to watch this. So all I have to do to figure out what the value of R is to have known conditions of pressure, volume, moles, and temperature. And I do. I know that 1 atmosphere of pressure at 273 Kelvin, which is STP conditions, will occupy 22.4 liters if I have 1 mole of a gas. So I'm going to plug all that data in and solve it for R. And I get this very, very small number, 0.0821. And notice all 4 of the units stay. It's liters times atmospheres over moles times Kelvin. Now that means that if you want to use this gas law, you have to have the volume in liters, so you might have to convert that. You have to have the pressure in atmospheres, you have to have moles, not grams, and then you have to have Kelvin. And if you don't have these units, you're not going to be able to solve the problem. Now here's an example. You can see an aerosol can here. We want to know what is the pressure in millimeters of mercury in a 750 ml spray can that contains 2.20 grams of CO2 propellant at 25 degrees centigrade. So all of these aerosol cans have a propellant in them, some gas that will carry out your liquid. The reason you shake up that container is because the liquid always settles to the bottom, and you want to try to get that liquid to come out as a nice spray. So an aerosol actually means a mixture where you have a liquid spread throughout a gas. So let's do some calculating. First thing we want to do is write down our gas law. And we want to solve it for our unknown, which is going to be pressure. So pressure, we'll go back on this, pressure equals nRT over V. And then we want to have all of our factors. Now we need nRT and V. Now N is moles, so I'm going to have to convert my 2.20 grams of CO2 to moles. So moles would be grams divided by the molar mass. Molar mass of CO2 is 44, and that gives me 0.0500 moles. So I'm keeping 3 significant figures. Now R is the gas constant, so I already know that. Here it is here. Now temperature, I need 25 centigrade converted to Kelvin, so I just add 273 to that. And I need the volume in liters. I'm going to have to convert 750 milliliters to liters. And then I plug it into my formula, and you can see that everything will cancel. Moles will cancel, liters will cancel, Kelvin will cancel, and I get an answer in atmospheres. And because my question really asks for the pressure in millimeters of mercury, I have to convert my 1.63 atmospheres to millimeters, and so I'm going to use my conversion factor, 760 millimeters to an atmosphere, and then I get a final answer of 1240 millimeters of mercury. Okay, looks pretty good. So you can see problems in the text and in Connect where you're going to have to apply the gas law. So you can solve this gas law for pressure, volume, moles, even grams, or even temperature. So I'm going to show you a couple of others to help you before you go to Connect. So here we have a question. We want to find the density of CO2 gas at non-STP conditions. Remember, if this was at STP, we would just look up the molar mass and we could use a 22.4 liters. But we can't do that now because we have a different temperature and pressure. So I'm going to take my gas law and I'm going to solve it for density. So we have to remember about density. So first thing I want to note is that N is moles, and moles is grams divided by the molar mass. So I can replace N with G over MM. Now gradually I'm going to come up with density now, so hang on. Then I'm just bringing up my molar mass. Now remember, density is mass per volume. So mass per volume is going to be grams per liter. So you see how by dividing by volume, I now get this factor. What I want to do now is get grams over volume, which is density. I want to get that by itself, so I'm going to have to divide RT out of there. And so I finally get density equals molar mass times pressure divided by RT. So I've just derived the formula. I know in the textbook they give you the formula, but you can always derive it yourself. Now I'm going to plug in my data, and let's see what we get for an answer. I get my molar mass, the CO2, so that's 44 grams per mole. You notice the per mole, the moles in the denominator. Because I'm dividing by R, I'm flipping those units. So now you can see that moles will cancel, and Kelvin will cancel, and atmospheres will cancel, and I'm going to be left with grams per liter, which is the density unit. And I wind up getting 1.70 grams per liter. You don't have to use the ideal gas law to find this density at a different temperature and pressure. An alternate way to do it would be to find the density at STP, and then we can find the density under these conditions using the combined gas law. Okay, let's take a look at another question now. Here we have a balloon, and the volume is 1.20 liters, 0.86 grams of gas in it, 1.1 atmospheres is the pressure, and it's at 27 centigrade. I wonder what gas this is. So let's say we had some possibilities. Maybe it's helium. Helium is used in balloons. Maybe it's oxygen. You could use oxygen in a balloon too. In fact, you would use any gas as long as it was less dense than air in a balloon. You know what happens if you blow up a balloon on your own and you let it go after you tied it off, of course? The balloon just sinks to the floor. And that's because you're breathing in a lot of CO2 into the balloon, which is denser than air. So that's not too helpful. So I wonder what this gas could be. Now, if we consider that the air has, let's say, an average molar mass of about 29 maybe, because it's mostly N2, which is molar mass of 28. That means as long as the molar mass of our gas is less than 29, it could be used in a balloon. So let's see, how do we figure out the molar masses? So I'm going to take my formula, and I'm going to find molar mass, which is in N, and I'm going to solve for molar mass. So let's watch how we derive this one. So N I know is moles, and moles is grams over molar mass. So I can replace N with G over MM. Now my point is to get MM by itself in the numerator. So to do that, I have to multiply by molar mass. So it appears up on the left, it will have disappeared from the bottom on the right. And then I'm going to have to divide by PV to get molar mass by itself. This is what I have then. Now I can just plug in my data and let's see what we get. So, canceling. Atmospheres would cancel. Liters would cancel. Kelvin will cancel. And I'm going to be left with grams per mole, and that is molar mass. So what do we get for an answer? 16 grams per mole. Now I wonder what common gas that could be. Well, as it turns out, that could be CH4, and that would be our answer. So you see, the ideal gas law has a lot of applications, and I've just gone through a few of them. So you're going to be doing some of these kind of questions on Connect. And so I'm going to also tell you for the exam coming up which parts of the interactive study guide to be viewing. And that's the end of the show. That is Dalton's law of partial pressures. And this has a lot of applications to medicine. You can see here a person is getting some gas, some nitrous oxide, being worked on. Right, so partial pressure of a gas is the pressure that each gas in a mixture would exert if it was by itself in a container. So here's our example. We have two containers. They're the same size container, so the volumes are the same. I'm assuming they're at the same temperature. And this container has a smaller amount of molecules. This one has more. So you see the pressure in here is 2 atmospheres, and the pressure in here is 4. And so the number of particles, 8 particles versus 4. Okay. What would happen if you were to combine all these gases into the same size container? So what would happen? The pressure would simply be the sum of the two pressures. And that's Dalton's law of partial pressures. So it means that if you have a mixture of gases in a container, the pressure of that mixture is the sum of the individual pressures. And they call the individual pressures the partial pressures. So here's the formula for it. The total pressure is equal to the sum of the individual pressures. Pretty easy. Now this diagram kind of shows you the same thing. We're at STP. We have 1 mole of pure gas in a volume of 22.4 liters. Will exert the same pressure as 1 mole of a gas in a mixture. So see how we have here 1 mole of nitrogen, 1 atmosphere pressure. They put different numbers of moles of gases, but the total was 1 mole. You still get the same total pressure. So the pressure that we get from a mixture doesn't depend on the particular gases that we have in the mixture. It's only the pressures of those gases. Now here's an example that they like to go through, and that's like scuba diving. When people are scuba diving, they're breathing a mixture of gases. Now if they just have compressed air, air is mostly N2. So what happens if somebody is down deep and they come up too fast? Well, when they dive down in the ocean, the pressure on them is really the pressure of the water, which is much greater than air pressure. And that can cause some of the nitrogen that they're breathing to dissolve into the bloodstream. If they come up too quickly, they're going to get the bends, which is really nitrogen gas bubbling out within the joints of the arms and the legs. And they call it the bends because you can't bend your arms and your legs because of the pain. And it can be fatal. So when people come up from diving deep down, they have to go very slowly. And so that as they rise, the pressure will be released and the nitrogen gas will leave the bloodstream and enter back into the tank. This slide here shows you the partial pressures of the gases in the air. So nitrogen is pretty much about 80% of the air. So then it makes up about 80% of the air pressure. So here's the pressure of the nitrogen. Here's the pressure of the oxygen. See, that's 21%. And carbon dioxide, about 0.8%. All the other gases are very low. Total pressure, 760 millimeters of mercury, 100%. Now, let's say they were going to solve a problem about using Dalton's law. The law is so simple that all the problems really involve is usually give you different pressure units and you have to either add them together, or they might give you the total and they want to know one of the pressures that's missing, but again they try to mess it up by giving you different units. So that's what they're doing here. So you have a scuba tank contains oxygen with a pressure of 0.450 atms and helium with this pressure. You notice millimeters of mercury. Okay, what's the total pressure in millimeters of mercury? So what are you going to have to do? You have to convert your atmospheres to millimeters. And so that's what they're doing right down here. 400.450 atms, 760 millimeters per atm, and that's the pressure of the oxygen. And then once you get that, you can add it to the pressure and of the helium, and that's what they're doing, and that's our final answer there. Here we go. My circle didn't work out too well there. All right, so here's one for you to try. For a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8.00 atmospheres. So that's the pressure of the mixture. If the oxygen has a partial pressure of 1280 millimeters of mercury, what's the partial pressure of the helium? And the answers are all in millimeters, so they want you to get the answer in millimeters. So what are we going to have to do? Why don't you take a shot at it and just pause the video and come back and see the solution. That's going to be similar to what we had before. We're going to have to convert our atmospheres to millimeters, and that's what we're doing down here. So that means the total pressure is really 6080. Here's my 6080 millimeters of mercury. And then I can subtract the pressure of the oxygen from that, which is this guy here. And then I got that for an answer. It's pretty straightforward. Now this is where the medicine kind of comes into play. We talk about oxygen and carbon dioxide in the blood, and that's actually measured by the partial pressures of each. And so in this diagram here, we have in the lungs, oxygen enters the blood and CO2 leaves it, and in the tissues, oxygen enters the tissue and CO2 leaves the tissues. And this is supposed to represent the tissues here, and these are the alveoli in the lungs. And so the PO2 less than 30 in the tissues, and PO2 is 100% in the alveoli. So your oxygenated blood is going to the tissues, and the reason the oxygen enters the tissues is because of the pressure difference. So oxygen flows into the tissues because the partial pressure of O2 is higher in the blood and lower in the tissues. And the gases flow from high to low pressure. CO2 flows out of the tissues, again because of partial pressure differences. And we can see that here in this slide. Oxygenated blood, let's say we have 100, let's say it's millimeters of mercury, and CO2 it's 40. And then we have deoxygenated blood, a lot less pressure, and you see the CO2 is up a little bit, not much. So, but in the tissues, it's different. So why does oxygenated blood release oxygen to the tissues? Look at the difference, 100 to 30. So it's going to flow from the blood into the tissues. Now for the CO2, it's 50 or greater. It's going to go then from here back into the deoxygenated blood, and you see it's even less as we go to the lungs. That's the reason why we can get these gases in and out, because of the pressure differences. And this graph or chart is telling you the same thing. Inhaling the air, here's the pressure of the nitrogen. Exhaling it, a little bit, kind of the same. So that means that some of the nitrogen is staying in our lungs, some of it might be dissolving into the bloodstream, but it's not having much of an effect because it's really a very small amount of it. And in the alveoli, inside the lung tissue itself, you see that it's a little bit greater than the expired air, but not too much of a difference. Look up for the oxygen now. You breathe in, here's the pressure of the oxygen, 160. 116 is what you're exhaling. That means the difference here is going into the tissues. So the alveolar air has 100 for the millimeters of mercury. So you notice that's that's less than what you're expiring. For the carbon dioxide, you're breathing out, you're breathing in less carbon dioxide, breathing out more. That's what these numbers are telling you. And that's the end of the show.